accepting our invitation, sir.
You are welcome.
So, all set, sir. If you say yes, we can start the proceedings of the program.
Yes.
Okay. Nandini,
Yes, sir.
you can start the program.
A good day to everyone. My name is Yadava Nandini, pursuing master's degree at IIIT Hyderabad. I feel honored to extend my warm welcome to all present here. On behalf of IS Shakti, IIIT Hyderabad student chapter, I want to take this opportunity to welcome our honorable speaker, faculties, participants from the academia, the research fraternities, industrial professionals, and all the students to join the online session on the topic seismic resilient or robust structures. I would like to introduce our guest speaker, Dr. N. Subramanian. He is an award winning author and mentor. He is currently working as a consultant engineer, Maryland, USA. With the doctorate from IIT Madras, he worked with the Technical University, Berlin, and the University of Montessori, Munich, for 2 years as an Alexander von Humboldt Fellow. He has over 47 years of professional experience in consultancies, research, and teaching in India and abroad, and has designed 800 projects and developed several software packages. He has authored 25 books and over 325 pages. He is the fellow of many professional organizations and worked as a vice president of Indian Concrete Institute and the Association of Consultant Engineer India. He is the recipient of several awards, recognitions, including the Fellow of Indian National Academy of Engineering, the 2024 Edmund Friedman Professional Recognition Award of American Society Civil Engineer, Honorary Fellow of Indian Association Structural Engineers, Association of Consultant Engineer India, Gaurava Award 2021, ICI L&T Lifetime Achievement Award, etc. He has been awarded ACCE Nagadi Award for the best publication for 3 of his books. He serves as an editorial board review committee for several international and Indian journals. This is the brief introduction to the speaker. Now, before we start an event, a small announcement to all the participants. If you have any questions, doubts, or clarifications, please do type your queries in the chat box only. We will have sufficient time at the end where Dr. P. Praveen Kumar Venkatarao, Faculty Advisor of Student Chapter, will be the moderator. Now, without any further delay, we'll turn the time over to our speaker. Sir, over to you.
Thank you very much, Ms. Yadav Nandini, for a great introduction. Good evening to all of you and happy Holi. I think today is Holi. So in spite of Holi, I think you have come to listen to
Thank
me.
you, sir.
Thank you very much. And I would like to thank, first of all, Dr. Praveen Kumar Venkatrao for inviting me to this to give this talk to you all. And first of all, I would like to congratulate Praveen Kumar Venkatrao, who is doing a lot of work in the seismic design area, especially in brick and reinforced brick structures. I think he sent me a paper recently published by him. It is a very voluminous paper and considers so many aspects of brick structures in earthquake-prone zones. Congratulations.
Thank you. Thank you for your blessings, sir.
And today I am going to talk about seismic resilient and robust structures. All of you know that seismic design is entirely different from other design due to other forces like live load, dead load, wind load, etc. It is because we don't know where an earthquake will strike and what will be its magnitude and other characteristics. And also it is a very high force compared to wind or other loads. So what we do, we are reducing the earthquake load by a factor R. Of course, that also is not scientifically determined. It is based on some experiments and also from experience. And then we reduce the load and then apply it. And of course, we think that the ductility and other factors will help us in keeping the structure safe. But we know that we are designing for a reduced load, and we don't know what will be the earthquake. So the codes previously they used the deterministic approach to determine the force, and also there were two different earthquakes for earthquakes that are considered, that is actual earthquake and then design earthquake. So in the design earthquake, we are reducing the earthquake force by 50% in our codes, and in American codes it is 2/3 of the actual force. But once again, we don't know what will be the actual earthquake that is going to come, and hence what we do is we detail the structure properly and this is the approach adopted in our codes. But still, if there is a higher earthquake, there will be heavy damage to structure, and that is where these seismic resilient or robust structures come into play. So I am going to discuss about these things in this lecture. So the things which we are going to discuss are, first of all, I have told you that the seismic damage will be there. So we will consider those seismic damages, and then seismic design of buildings. As I informed, detailing is very important as design, and we will see some of the seismic moment connections in civil structures, and then we will see what is the difference between robustness and resilience in structures, and let us define what is resilient design, and then increasing the robustness of buildings using base isolation, energy absorbing devices, and we will also discuss about some simple methods of increasing robustness. And finally, we will consider the foundation design. So seismic design damage, you might have seen a lot of pictures like this, but this is a very nice picture which happened in Bhuj earthquake in 2001. This is a partially open ground floor building. You see that not only the building collapsed, it also split at the middle. So due to this, we always say earthquakes do not kill people, but improper design and detailing do. What are the factors influencing the seismic damage? These are the some I have listed some of these factors: peak ground acceleration, amplitude, duration and frequency of ground vibration, magnitude, distance between epicenter and site, geographical conditions, soil properties at the site and foundation type, and type and characteristics of the building. And that shows the previous one. It shows the damage to a steel building in Mexico City, 1985. This Mexico City earthquake is a interesting one because that site, the entire Mexico City, is located on a tank bed or lake bed. So it will amplify the earthquake forces. So let us see some of the damages which happened in January 26, 2001 Bhuj earthquake. It killed 20,000 people, injured 167,000, and destroyed 340,000 buildings. And property damage was around 4,519 million. So this shows two 5-story buildings collapsed due to soft story effects. And this shows the short column effect in a warehouse in Candela. So during the past earthquakes, the several damages were observed, and it shows very poor performance of buildings due to several reasons. Of course, you can refer to table 5 and 6 of IS 1893 part 1 for all these failures, why these failures are occurring, etc. And I have shown some of the examples: the shear critical columns, weak columns and strong beams, sudden change in stiffness, soft story, and this shows the open ground floor failure. It completely turned by the side during the Buji earthquake. And plan and vertical irregularity. This shows the example of a plan irregularity. And torsional irregularity. This shows the failure of an L-shaped building, which introduces torsion, unconfined beam column joints, weak stories, floating columns, etc. So several failures of columns. Actually, columns are very important in any design, especially in earthquake design. Unfortunately, people do not consider the design of columns carefully, and they provide very thin columns, and also they do not detail them properly. So due to this, there can be several failures, buckling of column reinforcements, and insufficient transverse reinforcement in beam column joints. And they don't do this because it is very difficult to provide this transverse reinforcement. And poor anchorage of beam bars in beam column joints, provision of strong beams and weak columns, and then improper detailing in plastic hinge zones. And I have shown some of the failures here. And this is a punching shear failure and collapse of intermediate story, and then complete failure, and then unconfined beam column joints. And I want to show this particular slide. This shows the columns, two columns in the same building during the 1971 San Francisco earthquake. This shows the building in which these columns are situated. And this building had a 600 mm drift in the first story. You see this drift here. And the rectangular column of this building, you see it is completely collapsed. And you see that lack of lateral ties or the spacing of lateral ties is very large. Whereas in the same building, the same another column, which is a spirally reinforced column, because it is spirally reinforced, the spacings are very close, you see here, and it is still carrying the load. Because I just wanted to show the other failures, pounding failures, soft story I already discussed, and this shows the failure of a column due to soft story and also collapse of water tank. And since Professor Rao is there, I included this slide only yesterday. This shows the failure of infill walls. So normally you see that it is common to have infilled walls in framed structures, assuming that it improves the behavior under seismic load. This is true only when the earthquake load is small. And also the masonry remains largely intact. Actually, it is better to brace masonry buildings with reinforced concrete structural walls or reinforced brickwork. Actually, the framed structure is relatively flexible and somewhat ductile, while unreinforced masonry is very stiff and fragile and may explode under the effect of only small deformations. At the beginning of an earthquake, masonry carries out most of the earthquake action, but as the earthquake intensifies, the masonry fails due to shear or sliding. The appearance of diagonal cracks in this masonry is characteristic of a seismic failure. Actually, when you provide stronger columns, masonry will completely collapse and fall out. But when you have weaker columns, masonry will damage and shear the columns, leading to collapse. So we will just now go to seismic design of buildings. Of course, most of you will know all these codes: IS 1893, IS 13920, IS 18168, and then IS 4326. All these are Indian codes related to seismic design. And one more thing is these codes are often revised. You see that this code was introduced only in 2023, and these two codes are also under revision. So we will just see the lateral force resisting systems of concrete. shear frames, which are good, and then moment resistant frames, which are often adopted, and also braced frames. Some people may think how braced frames can be adopted in concrete, but concrete braced frames have already been adopted and used in India as well as USA. And then these are steel structures. Once again, steel shear walls. Of course, we can also have steel shear walls as well as concrete shear walls, and braced frames and moment resistant frames. It is in order to have better performance during earthquakes, we should have rectangular cross section. Of course, square is better, and the best is circular, which is not adopted because of some practical reasons. If you have elongated rectangle, it is very bad. Worst is T sections or L sections. It is because there will be damage at the re-entrant corners. So it is better to have simple and regular plans. So planning is also very important in earthquake resistant design because the effect of asymmetry will induce torsional oscillation structures and stress concentrations at re-entrant corners, like what you have seen in the last slide. And there are several irregularities that have been discussed in class 7.1 of IS 1893, and they are I have divided them into planned irregularities and vertical irregularities. You know most of these irregularities. I will just show some slides to explain these irregularities. I wanted to show this book. This is a seismic conceptual design of buildings written by Hugo Bachmann of Switzerland. It was published in 2002. Actually, all of you can download this on the internet as a PDF file. This is the link to that. Actually, this is a very good book which shows how to adapt or design buildings, especially conceptual design. It is mainly for architects. And he says, even the cleverest calculations and detailed design cannot compensate for errors and defects in the conceptual seismic design of the structural and non-structural elements. Actually, non-structural elements are also very important. And hence he says, close collaboration between architect and the civil engineer or structural engineer from the earliest planning stage. So you have to collaborate with the architect. It is better if some of you are going to practice, it is better to present this book to your architects so that they will know the importance of the planning in the earthquake design. These two I have already explained. T-shaped and L-shaped buildings are very bad, and also U-shaped or cruciform plans or other complex shapes. And setbacks, multiple towers, split levels, usually high story in the ground floor or low story in ground floor or other floors, or outwardly uniform appearance but non-uniform mass distribution is also very bad. Of course, you can see class 8.1.3.3 of IS 16700 for more discussions on buildings with multiple towers and backstay effects of these buildings. And we should also avoid buildings with abrupt changes. So these soft lower levels, large openings in shear walls. The shear walls is not continuous up to the foundation, and interruption of columns, that is floating columns, interruption of beams. Some beams are removed, and then openings in diaphragms, and shear walls in some stories, moment resistant floors in other stories, interruption of vertical resisting elements, and abrupt changes in size of the members. Actually, that is also very important. A drastic change in mass and stiffness ratio, which I already discussed. So can we, so many people ask, can we design to resist earthquakes with no damage? Yes, we can design structures to resist structures with no damage at all. However, it will be prohibitively expensive and unwarranted for small probabilities of occurrence of such catastrophic earthquakes. Instead, the objective is to reduce the probabilities of fatalities to an approximately small value. That is what we are considering in the codes. So the earthquake design philosophy I already explained earlier. That is, during minor and frequent earthquake, there should not be any damage. Moderate earthquakes, there can be some damage, but there should not be any failure. In major and infrequent earthquake, there can be major damage, but it should not cause a collapse. Hence, design is done for much smaller forces than actual seismic loads. Note that this approach is different than that adopted in the case of wind, dead, live and other loads, where the structure is designed for the actual loads. As I already told you, till now it is not possible to predict where the earthquake will strike and what will be its magnitude or intensity or any other characteristics. So we designed the structure for reduced earthquake load and thinking that the following contributing factors will prevent the collapse of the structure. That is overstrength, redundancy and ductility. So it is shown here in this. So due to ductility, we are reducing this much, and due to redundancy, we are reducing this much, and due to overstrength, we are reducing this much. Actually, the design force is this, whereas the actual force may be this one. So many people think of only strength, but also deformations are also very important. These allowed drifts are given in IS 16700 to 2023 class 5.4.1. Total drift at the topmost floor h by 500. That h is the total height. For a single story, the drift limit may be relaxed to hi by 400. For design earthquake force, the maximum interstory drift should be hi is the height of the each floor by 250. And our codes also advocate strong column and weak beam concept. This is a picture really shown here. So we should not adopt this, and we should adopt strong columns and weak beams. But normally, we find that many people don't adopt this. Why strong column weak beam? It is because this concept will make plastic hinges to form in the beams, and only at the end plastic hinges will form at the columns. So I always stress that the detailing is very important. It is as important as the design as well as planning. So this shows the confinement steel in columns. We should have the lateral ties at regular intervals, not like this, and also have 135-degree hooks at the ends of the lateral ties. This is a very nice figure which I have taken from Poultry and Lageron in 2008, published in the Journal of Structural Engineering. So if you provide such an arrangement, you will have confinement of the concrete and get better strength. And also it is important to have closely spaced transverse segment at column plastic hinge locations and to have 135-degree hooks in the earthquake zones. And when you have a mezzanine floor which will produce a short column effect, it is better to provide the closely spaced ties throughout the column, whereas in the regular column you provide this closely spaced reinforcement only at near the junctions. And this I told you that many people don't provide this because of the practical difficulties. Actually, these 135-degree hooks and closely spaced ties in the beam column joints resist the ill effects of distortion of joints and prevent failure of joints. And the shear walls, when many people they simply oppositely place the shear walls, it is not correct. You have to position the shear walls equally on both sides. So symmetric location of shear walls along the perimeter of building is desirable. If it is not possible to provide at the ends, it is better very close to it is provided very close to the ends or around the staircase wells. So this shows the detailing of shear walls as per IS 13920. I have shown these figures, and it shows the wall failure in 2021 Christchurch earthquake in New Zealand. Here also, it is important to have closely spaced transverse transponders space at S is less than 5D, where D is the diameter of the bar in structural walls, wall boundaries, and also in columns. And coupling beams are better than shear walls, or shear walls connected with the coupling beams. This shows the conventional reinforcement in the coupling beam. These are conventional reinforcement. And Professor A.R. Santakumar of Anna University is retired. He developed this diagonal reinforcement when he was working for his PhD with Professor Paule of New Zealand. And this shows the failure of the coupling beam with normal reinforcement. So the conventional detailing actually during the 1964 Alaska earthquake. It is a 14-story apartment building, and this actually wherever I have taken figures or some important information, I have given the references here. You can check it later on. So now we will go into some seismic moment connections in steel structures. Seismic moment connections in steel structures, three strategies are always followed: toughened connections, strengthened connections, and weakened connections. We will see these things in the next few slides. I would like to inform about an important document, that is AASC code 358, released in 22. It is under revision once again. Pre-qualified connections for steel special moment frames for seismic application, that gives details and design of several, that is 12 connections. They have been tested, and it also gives the design equations, etc. So if you are using those connections, you need not bother about the failure of the structure. Actually, the main aim is to ensure plastic hinge locations away from the joint, because joint is the most important the location in any structure. So we should see that the joint is not affected. So using cover plates, using grips, and using side plates, and using hatches, we are trying to locate the plastic hinge away from the joint. So at this location or away from the joint. So I just wanted to show 2 or 3 connections which are given in that code. This is an interesting connection. Actually, here some cast steel brackets are used. You see these are cast steel and not steel connections, and also they prevent the plastic hinge to form at the joint but away from the joint. So this shows the actual connections at site, and it shows the use of that connection in a structure. I think it's a composite structure. And another thing I already told is a weakened connection. Actually, this connection only was first developed in the USA. You see that the beams are cut like this in the form of an arc. That radius is given here, and the details are given here. And this is the protected zone. And instead of the cuts, they have also, some researchers have also tried making holes regular holes or increasing the hole diameter or having a straight cut or tapered cut, etc. And this shows the connection type and relative cost. So if you don't have any other connection type like this, then the relative cost will be 1. And if you have a radius cut dark bone connection, the cost is 1.71. This cost increase is due to the labor involved and also extra fabrication. And constant or tapered out to one dark bone will cost 2.18, cover plate 2.5, and so on. Side plates 3.96, and the top and bottom haunch will be the costliest thing. So this is a example, actual example of a side plate connection. This is a patented connection. Okay, now we will discuss about robustness versus resilience in structures. Robustness is defined as the ability of a structure to withstand events like earthquake, wind, fire, explosion, impact, etc. without being damaged, whereas resilience refers to the capacity to recover and return to full function after experiencing damage from an extreme event, focusing on the ability to bounce back after disruption. Yeah, that is in pictorially shown here. This is the quality of the structure 100%, and it drops to 50% after the earthquake, and then it bounces back after the earthquake. Thus, robustness is about preventing significant damage in the first place, whereas resilience is about recovering from that damage quickly. Structural robust, you may be interested to know that the robustness criteria, that is resistant against fire, blast, and impact, are being introduced in the 5th revision of IS 456 in class 9.6. Actually, there is a key difference between robustness and resilience. Robustness is focuses on damage. It minimizes the extent of damage, while resilience focuses on the speed and effectiveness of recovery after damage occurs. And robustness is considered as a proactive approach, designing structures to withstand extreme loads from the outset, while resilience involves considering recovery strategies after an event has happened. We will see later how to have this resilience or robustness. So examples are robustness design is a building with redundant structural elements and strong connections to prevent localized collapse in the case of an earthquake, whereas a resilient design is a building with easily replaceable components and rapid repair mechanisms to quickly resume functions after natural disaster. So I just wanted to show this example of a resilient structure. This is a 102 story and 443.2 tall building in USA. So it is one of the 7 wonders of modern world by the designated by the American Society of Civil Engineers. And you may be interested to know that it was designed and built before the use of computer software. On July 28, 1945, a B-25 missile bomber crashed into the north side between 79th and 88th floor, and the building survived the impact. Since 2011, it is powered by 100% renewable wind energy, and it is aiming to achieve carbon neutrality by the year 2024. So now we will see what are resilient designs. Actually, the code required minimum design for earthquake resistance is based on balancing economy and life safety. As I told that we are not designing for the full earthquake force. So we also design lateral system with certain components intended to absorb earthquake energy through inelastic response to prevent collapse. So let us see the number of fatalities between 2020 magnitude 7.0 Haiti earthquake, where 200,000 people died, and the 2011 M6.2 Christchurch earthquake in New Zealand, where only 185 people died. Clearly, a ductility-based seismic design enforced by the codes, standards, and inspections is successful at providing the life safety. It is considerably reduced. Of course, it is slightly higher earthquake. But in Christchurch Central Business District alone, more than 1,400 buildings were demolished because of the damage. At the time of earthquake, the population of Christchurch was approximately 350,000 only. Think about the damage in larger cities like San Francisco, Los Angeles, or New Delhi, or any other big city in India. The number of buildings that would be damaged and then required either long and costly repair or demolition would be much greater. So structural engineers should initiate discussion related to the functional recovery objectives early in the design process. They should clearly communicate to the owner that meeting a code minimum will result in damage that could require repairs that render the building partially or completely unoccupiable for several months or even years following an event for repairs, complete repairs. So the functional recovery objectives are critical in selecting the lateral and gravity systems. Different lateral systems like shear walls, brace frames, moment frames have different functional recovery characteristics. Shear walls and brace frames tend to have lower relative story drifts, but they also have higher floor acceleration. Moment frames tend to have higher relative story drifts, but lower floor accelerations. Both structural and non-structural damage are affected by the dynamic characteristics of the lateral system. So very stringent functional recovery objectives may require the use of seismic isolation and supplementary viscous dampers. We will discuss about this isolation, seismic isolation and dampers later. So how do we select the lateral system? High ductility system will incur significant damage in a design level or greater earthquake. The building code IBC and AAC 7 provisions that improve functional recovery requires designing for higher forces and decreasing the allowable drift limit. I always insist on decreasing the allowable drift limits, which is very important. These requirements improve functional recovery, but they also have cost implications. So you have to discuss about the cost implications with the client. Strength and stiffness are two controls that structural engineers have that could affect functional recovery, but they are not the only controls that are available. So I am taking this slide as a concept. You see there are two systems, reinforced concrete shear wall and coupled reinforced concrete shear wall. See, these red zones are the failure zones. So the typical reinforced concrete walls are designed to yield at the base of the wall, which can be very difficult to repair. Whereas in the coupled wall system, the damage is focused in the coupling beams, which can be repaired or replaced following a significant seismic event. It is easier to replace or repair these beams rather than these shear walls at the base. And one more important way to enhance functional recovery at little extra cost is use a lateral system with a replaceable fuse. These replaceable fuses are designed to absorb earthquake energy in a component that is easily repaired or replaced. For more information, you can see these references. So this is an example of this. So usually in a steel moment frame, we saw that by using a system which can place the plastic hinge away from the joint. But once again, it is very difficult to change the beam after an earthquake in which the beams are affected. Whereas if you have a replaceable fuse, these after earthquake, these fuses only will be affected, and you can easily replace them with little or very small cost. So that is the concept. And based on this concept, a moment connection has been um, used or developed, and this is explained in AIC 35822, and this is a patented connection that has plates to connect beams to the columns. You see, these are the fuse plates. This is a Dura fuse connection. This connection has a steel fuse plate at the beam bottom flange that limits the amount of force that can develop at the face of the column. The shear yielding mechanism of the fuse is not susceptible to local buckling, so large rotations can be accommodated without much problem. For I-shaped column, the column has cover plates on each side. These are cover plates that are fillet welded to the column flanges. Four external continuity plate that extend past the face of the columns are fillet welded to the column cover plates. The column has a single plate shear connection with horizontal slotted holes that is fillet welded to the column face. The beam web with standard holes is attached to the single plate shear connection with pre-tension bolts. So you can see more information about this Durafuse moment connection in AISC 35822. So another concept, this is for braced steel frames. So you see, these are the damage. Once again, these are the portions which will be damaged in a concentrically braced steel frames. And this is a buckling restrained brace that yields in tension and compression. In a conventional frame, braced frame, it will yield in tension, buckle in compression, causing damage to several components. But more resilient option is a buckling restrained brace frame. We will discuss about the buckling restrained braces later. They are economical lateral systems that have many performance benefits over a concentrically braced steel frame. Here, the damage is confined to the BRB, which can be replaced following a significant seismic event. So another system, this is called as rocking braced frame. So here in this rocking brace frame, the brace frame is allowed to rock at the foundation level. So it can just rock. The frame shown here also has the advantage of being able to self-center because of this high strength cable. The frame recenters itself using a tensioned high strength cable, and rocking brace frame is likely to increase the initial frame cost, but the benefits to functional recovery after an earthquake would definitely offset the upfront cost. The damage is absorbed in the yielding fuses on either side of the frame, which are designed to be easily replaceable. So the several resilient components have been developed, and some of them have been used in other parts of the world, especially in New Zealand. I am going to show some of these examples here. This is a replaceable frame shear links, precise ring feeder hold down springs. The key difference is the resilient components as above are integrated as an accessible, replaceable component with sufficient ductility to dissipate seismic energy. Some more examples are shown in this. So we have already discussed about the buckling restraint frames, braces, and compression and tension yielding energy dissipators, sliding friction joints, and then lead rubber base isolation bearings and concave friction slider base isolation, which we will discuss later. The cost premium for resilient building design is typically found to be 1 to 3% of the total construction cost, while base isolation is more expensive, that is 5 to 7% of the cost. Two more examples, U-shaped flexural plate, which will yield during earthquake, and energy dissipating steel plate connectors. This will also yield during the earthquake, which can be easily replaced. Let us see the actual examples of using these systems. This is a yielding plate which has been used in this super large 7 building in Christchurch, New Zealand. This is a precast concrete walls are coupled with a ductile weld plate connectors of thickness 10 to 20 mm. The plates can be accessed and replaced if necessary. And actually, in this example, they are hidden from the view. All the precast walls in the longitudinal direction were detailed to allow for ductile response at the base as required by a coupled wall system by long debonded lengths of starter bars connecting the panels to the foundations. Actually, the hysteretic energy during the earthquake is dissipated by the plate yielding. You see here. They are acting as yield diffuse. Each connector is welded to cast in plates. So this is another example. This award-winning building at Wellington, New Zealand has a rocking concentrically braced frame with ring feder hold-down springs. These are the ring feder also hold-down springs. These springs dissipate energy through friction between nested rings with a conical interface. These springs combined with concentric braced frames are designed to rock and uplift at the base, dissipating energy and restoring the frame to vertical. The springs have pre-compression applied to counter uplift forces due to seismic actions. In some cases, additional post-tensioning can be applied to supplement the spring component, spring compression. So another example, this is a wooden structure in New Zealand. This award-winning Nelson and Marlborough Institute of Technology building in 2009 has an all-timber multi-level post-tension rocking wall structure combined with a U-shaped flexural plates. I have shown this U-shaped flexural plates in an earlier slide. And these are compression and tension yielding energy dissipators. These plug and play dissipators, that is another name for this, are mild steel bars which yield in both tension and compression. Actually this is with and inside a steel tube filled with grout and epoxy, which is similar to the buckling destined braces. The dissipators activate with the opening of a gap and are typically used in rocking structural system, providing ductility. The yielding and plastic straining is concentrated over a defined length inside this through the use of reduced steel area. Another interesting example is a terrace stage one, once again from New Zealand. Using these shear joints, the seismic energy is dissipated by controlled sliding of tensioned steel plates with minimum damage to the structure. It is so designed that the beam is pinned. See, it shows the structure. This shows its joint, and this shows the concept of the design. You say this is a point of rotation at the top flange, and it is connected to the bottom flange and the bottom of the web by unique asymmetrical friction sliding detail. You see this is a friction sliding detail which functions via rotation generated by seismic moments. So this joint dissipates energy by opening and closing each time pivoting about the top flange connection. So these joints are rigid under working load, slide under design level earthquake, and return to rigid connection at the end of the earthquake. So that is the advantage of this joint. So we have seen about the resilience. We will see now how to increase the robustness of the building. The main system which increases the robustness is the base isolation system. So this shows the schematic of the base isolation system. It is a significant development in the earthquake engineering in the past 35 years. It provides the design profession the ability to design a building that is operational after a major earthquake. So this is a conventional structure which which is deflecting and drift is very high, whereas in a base isolation system, only these isolators deform, whereas the structure is prevented from any deformation. Of course, very little deformation. Some of the examples: William Clayton Building in New Zealand is world's first base isolated building. Isolators up to 1600 mm diameter and around 600 mm height are currently available, which is capable of sustaining 220 mm axial load and 80 mm shear displacement. The performance of this technology was verified during several earthquakes. For example, 1994 Northridge earthquake of California and 1995 Kobe earthquake of Japan. Many of you may be interested to know that these two earthquakes in USA and Japan are very important, because from those earthquakes we learned a lot of behavior of structures and developed a lot of systems. And also the 2008 Sichuan earthquake in China. For example, a California hospital remained operational, unlike other conventionally built structures in the area. And similar thing happened in the Sichuan earthquake in China, as well as the recent, I think 3-4 years back, the Turkey earthquake. So other examples, this shows the base isolator being installed during a seismic event. Every isolator will extend in any direction by 21 inches. The cost of this base isolation, I already told you that it will be 5 to 7% of the total cost. San Francisco Airport International Terminal is the world's largest base isolated building, and Christchurch Art Gallery in New Zealand is another example. And I have taken, there are only few examples in India, so I just wanted to show these two examples. The 300-bed district hospital in Bhuj was the first in India. It is installed with 280 lead rubber and sliding bearings. This was constructed after the Bhuj earthquake in January 2002. This is a recent example of the Indira Gandhi Hospital building in New Delhi. It is a major base isolated hospital building project built by CPWD in 2024. Of course, there are different types of seismic isolators. You can read about them in my paper published in CE and CR in 2024. But mostly we will be using the bearing type seismic isolators only. So that can be divided into elastomeric or sliding bearing. So we will see about these two in the next slide. This is a base. These are the two types of base isolators. This is lead rubber bearing. That is, this is a lead at the circular pin at the center, and these are steel plates, and rubber are alternatively used in this isolator. So once again, similar thing, but without that central pin. Base isolator may be either coiled springs or laminated rubber bearing pads made of alternate layers of steel and rubber, and have low lateral stiffness so that they can easily slide. This is a friction pendulum system. There is a ball, and there is a curved top surface. So this will move like horizontally. This is found to transmit lower seismic forces into the structure compared to the lead rubber bearings they found during the earthquake, but the displacement are proportionately larger. This shows the example of the lead rubber bearing. Actually, you cannot use this lead rubber bearing in all circumstances. For example, you see in the normal soil, without isolation, you will get the base shear, very high base shear. But whereas after providing this, the base shear is much reduced. But whereas if you are having soft soil, if this is in the stiff soil, it is reduced, but in the soft soil, the base shear is increased. So especially in the Mexico City, places like Mexico City, you should not use this kind of base isolation. Because recently, BIS has released a code, IS 1893 Part 6, for this base isolated buildings. There are several other international codes also. This IS code provides guidelines for the estimation of design lateral force and displacement to be considered in the design of buildings with base isolation system, methods of structural analysis to be adopted, and guidelines for testing of seismic isolation devices. According to the standard, it is very important to know even base isolated buildings have to be provided with the proper ductile detailing. That is the very important thing that is mentioned in this code. So they are, of course, you know that they perform better in during moderate or severe earthquakes. So we will now consider energy absorbing devices. They can be used along with the base isolation systems also. So what are these distribution? It is emerging as a technology that enhances the performance of buildings by adding damping to the building. So these devices add damping to the buildings. So the commonly used dampers are listed here. So most used is viscous dampers. They consist of a piston cylinder arrangement filled with viscous silicon-based fluid which absorbs the energy. There can be friction dampers or hysteresis dampers or viscoelastic dampers also. And other types of dampers, very important, is tuned mass dampers. They are extra masses attached to the structure by spring dashpot system, and they are designed to vibrate out of phase with the structure so that the effects or earthquake effects on the structure are reduced. And we can also have tuned liquid dampers and hydraulic activators. Why should we use the dampers? Because they result in reduced displacement, decreased base shear, and much lower acceleration forces due to gravity in the structure. The equipments keep working and people are not injured. So this shows the cross section of a viscous damper, and this shows the such a viscous damper placed in a building as a bracing. This shows the example of the pendulum type viscous damper, which is placed in the Taipei 101, the world's second largest building. This tuned mass damper is 18 feet or 5.5 meter diameter, 730 ton, and acts like a giant pendulum to counteract the building movement. And it reduces this way due to wind by 30 to 40%. The cost was for $4 million. Of course, compared to the cost of this building, this $4 million is not much. And also, although this was considered for the wind effects in this structure, I think a few years back there was an earthquake, and this pendulum also acted as a damper during the earthquake. Actually, we were talking about the buckling restraint brace. This shows the cross section of the buckling restraint brace that is used. So the one such thing is a core. The steel core is placed inside a tube, and then it is which is filled with mortar. So it was introduced by Takeda in 1976 and others in 1976, and deals with the buckling problem of tension and compression steel bases. Actually, the original concept was developed by engineer Sridhara of Bangalore. Actually, he came to my office. Of course, he is no more. He came to my office probably 25, 30 years back. and he showed a demo of this this system. He called it as a sleeved column concept. Actually, there was a circular tube, and inside he placed a vertical round bar, and then you know that when the load is applied not to the tube but to the rod. So you know that the buckling of the rod will be equal to pi square A by L square. But after it buckle, so it will touch the surfaces of the tube, and then it will take more load than the P critical load. So this is the concept developed by him, and based on that, these buckling resistant braces have been developed in Japan as well as in USA. Several other researchers have developed different configurations. As I told you, circular core, cross and crosswise core, and linear core. This shows a cross core. Between the metal joint and the concrete, a suitable coating is placed, which allows the joint to slide relative to the concrete. This method of construction allows the system to accept axial, compressive, and tensile forces, which are received only by the metal link located at its core construction due to slippage. The outer mantle of the concrete is intended to limit the pre-bending length of the metal joint. So we will see simple methods of increasing robustness. So many organizations like ACI, ASE, ERI, etc. have disaster recognition committees to study the effects of major disasters on construction worldwide and identify potential design issues requiring code change. Actually, these committees, wherever there is an earthquake, they will go there, study the damages, and find out why the structures fail, and based on that, they will develop some systems. Actually, based on 14 different earthquakes in different countries, and combining the ideas of NATO in Japan 100 years a year, 100 years ago, and Sosen in the USA, they found out some astonishing facts. It actually that is reported in Bujol et al. In the recent paper, which was published in the Concrete International ACI. So a minimum area of structural wall in RC and structural steel buildings in areas of high seismicity will prevent collapses and reduce structural damage, thereby saving lives. It will also result in increased functionality of buildings and cities after earthquake, thereby reducing population dislocation and increasing community resilience. So they plotted the wall index. That is, wall index is defined as smaller of the areas of walls in two orthogonal directions plus 1/10 of area of masonry infilled walls. This is defined by them, divided by the total floor area. And similarly, column index is 50% of total column area divided by total floor plan area. So it was plotted column index to wall index. From this, you see, they plotted 1,600 buildings that collapsed. And see this, these damages are concentrated in this quadrant. That is where wall index is less than 0.25% and column index is less than 0.37%. And only 9 of the buildings with wall index greater than 0.2% exhibited severe damage. Only 9. Regardless of CI, reinforcement detailing or shaking intensity. Separating the data by earthquake site does not change the conclusions, which is remarkable given the different areas are considered. Because these collapses are not in one place but in different areas of the world. And there is also a correlation between damages and PI, that is priority index. The priority index is nothing but wall index plus column index. So you see that in Chile, the percentage of severe damage is very near to 0, whereas in Turkey, earthquake in 2023 and Christchurch or other earthquakes, the damage is more than 50 to 70%. Despite the difference in design and construction practices, variation in ground shaking intensity, and plausible lack of uniformity in surveying practices, you see that there is a strong correlation between damage and the priority index. So they suggested minimum area of walls and columns to prevent damage in earthquake. In the absence of rigorous field quality control and exhaustive testing, adapt structural walls areas as below to get robustness. 0.2% into number of floors of the total area in each direction in buildings less than 15 stories, where n is the number of floors. And once again, detailing is critical in safeguarding against larger ground motion intensity and drift demands. It is better to lower drift demands to about 1% as deformation and drift can damage partitions, facades, and finishes. It will also result in increased functionality of buildings and cities after earthquake, thereby reducing population dislocation and increasing community resilience. In taller buildings, a wall density of 3% of the floor area was recommended by them in each direction as per the Chilean tradition. Actually, you may note that 2% of the wall area is recommended as per class 7.10.4 of the IS 1893-2016 but this is for RC frame buildings with open stories. So another robust building example, this is in Mexico City. As I told, there were these Mexico City buildings are located on soft soils. This building was built in 1956, which has a height of 188 meters and 44 stories. This withstood 7.9 earthquake in 1957 and also 8.1 magnitude earthquake in September 1985. The people in this working in this building saw collapses all around their building. Actually, many people are discussing about the structural items, but non-structural components are also important. I think in our course recently, the non-structural component design is also included because these components like cladding, interior finishes, mechanical, electric, plumbing systems, stairs, elevators, etc. Are important because the cost of the structural system is only 8 to 20% of the total cost, but the non-structural systems constitute 80% of the total cost. So now we will go for the foundation design, where bedrock is encountered at reasonable depth from the ground surface. It is better to transfer the load to the piles and caissons to the bedrock. In softer soil and where bedrock is not available at a reasonable depth, it is better to use a raft foundation. It is because tall buildings transfer large magnitude of loads to the ground and hence strong foundations are necessary for such buildings. In many cases, piles or caissons are combined with rafts, that is piled raft, to increase the foundation capacity or to distribute the load more uniformly to the piles and caissons. And we should pay special attention to soils that have low shear wave velocity, low internal damping, and then abnormally.
Speaker sir, sorry for the interruption. You can take another 5 minutes and then we can conclude.
I am coming to the end of my lecture.
Okay, sir. Thank you.
And an abnormally extended range of linear behavior, they produce unusual seismic site amplification and soil structure interaction effects. So, as I told, in the 1985 Mexico City 8.1 earthquake, the downtown buildings on lake bed vibrated to approximately 90 seconds. Its long natural period of around 2 seconds resulted in 6-story and 20-story buildings to resonate and collapse. But surprisingly, taller buildings suffered little damage. So, this shows 2 examples of collapse due to liquefaction foundation during the Turkey earthquake Richter 7.4, and during the Nikata earthquake in Japan with 7.5 Richter scale earthquake in 1964. So the how to mitigate these effects in sandy or silty soils. If water table is near the foundation level, install drainage to lower groundwater table and remove the pore water. Place the porous porous overburden over the site to produce over consolidation. If there are no adjacent structures, use vapor techniques to pre-consolidate the soil. If there are adjacent structures, they will be affected. Employ soil grouting or chemical injection to increase the shear strength of soil. Remove all deleterious soil and replace it better soil. Use pile foundation to rest the structure and sound strata. I think this is last slide. So I just wanted to talk about, introduce you about smart building technologies and adaptive materials. Disaster resilient structures often incorporate smart building technologies such as sensors, monitoring systems, and automated response system to detect and respond to potential disasters. Some structures incorporate adaptive materials that can respond to changing environmental conditions, such as self-healing concrete or shape memory alloys. The shape memory alloys, for example, nickel titanium alloys, are advanced materials with the unique ability to return to a predefined shape after deformation when exposed to heat or stress. Their super elastic and shape memory effects make them highly beneficial for earthquake resistant design and durable reinforced concrete structures. So, in summary, buildings with regular configuration, symmetric shapes without irregularities are best in seismic zones. As per seismic design philosophy in our codes, only a percentage of the earthquake load is considered using the response reduction factor R. Hence, during strong earthquake, the structure may be damaged but will not collapse. And AAC 35822 gives details of the design of several pre-qualified connections which will result in better performance of steel structures. And resilient design is required for better functioning of structures after earthquake. Examples of resilient buildings are those which incorporate special connect and detailing, supplemental energy dissipating devices, rocking systems, or base isolation techniques. Of course, several technologies I discussed, which include structural fuses, innovative dissipative steel plate connectors, etc. Of course, extra cost of base isolated systems will be 1 to 3%, base isolation up to 5 to 7%. Robust buildings or rigid buildings have a natural period less than 1.1 second, which may not be affected during natural disaster. Structural walls with about 2% area of the buildings in buildings with less than 15 floors and 3% in buildings greater than 15 floors are found to be robust. Some authors also suggest H by T ratio, where T is the natural frequency, to be greater than 45. Base isolation allows isolation of buildings from the earthquake ground motion. Various types of base isolators have been developed, and we have a new code, IS 1893 Part 6, which provides guidelines for base isolated buildings. Energy absorption devices can be used along with base isolation to mitigate the effects of wind also. We should also consider non-structural systems such as cladding, because they also have impact on post-earthquake recovery. Thank you very much for your patient hearing. Thank you.
Thank you so much, sir, for the detailed presentation. Nandini, it's over to you.
Thank you, sir, for providing valuable insights on the topic of seismic damage to the building. What are the factors influencing the seismic design, and the topic of structural design of building, details of reinforcement, details of shear walls, how beam strong column and weak beam connection principles, and the topics of difference between robustness and resilience, and foundation designs, how tall buildings can be designed for the foundations, and smart building technologies on these topics. Now we'll take the questions from the participants.
Okay, thank you. Sir, you can unshare your screen. Yeah.
Right.
Okay. Okay. Sir, we have few questions for you. So I'll
Okay.
read one by one. The first question from one of the participant is there any way to convert the weak column strong beam mechanism to strong column weak beam in existing framed structure? Is it possible?
We have to strengthen the column.
We have to strengthen the columns, right? Okay.
Actually, as I told many people, actually, I have written another paper on column design alone, because
Okay, sir.
in many places we have seen, of course, you also might have seen, they are giving importance to the beam and not to the column. Actually, column only is supporting all the load and transferring it to the foundation. So you
Right.
have to design the column properly and detail it properly. And also, especially in RC structures, when they are constructing the column, they are not vibrating properly because uh,
Okay.
the formwork is very high. So
Hmm.
they are not putting the, it is very difficult to put the
Right.
vibrators inside and then vibrate it. So after, if they remove the formwork, you will see a lot of unconsolidated concrete in the
Right.
columns.
Okay, sir. And there is another point also. If the columns are not stronger, then they may lead to the global failure, whereas the beam failure is a localized failure. Right. Okay. The second question is, how can infill walls negatively affect seismic performance if they are not properly designed?
I showed a slide
Yes, you showed us that.
of that because when there is an earthquake oscillation,
Right.
initially it will take. After some time, of course, IS code allows us to use a strut.
Strut
So that
model.
yeah, so that hinged strut. Actually, this is based on some experiments, etc. And they have also given an equation to find out the area of the strut, etc. But what happens is, during the earthquake, after 2 or 3 oscillations, these brickwork, if it is not reinforced, it will fail. And
Right.
it will be a catastrophic failure, and it will
Hmm.
not only damage the structure, but it will also injure the people who are
People,
inside the
right.
building.
Agree. Completely. Thank you. Uh, there is a question from one of the participant. The question is very lengthy. So I just want that participant to ask the question directly to the speaker. Miss Nisha, are you there? Would you like to ask the question to? Yes, please.
Good evening, sir.
Good
Thank you
evening.
for this wonderful session. So basically, on in ETABS, and it's flat slab system, 60 story, 180 meter, and I have used their core walls, coupled ductile coupled core walls. But the thing is, the parameters that I'm getting by equivalent static method, such as displacement, it's coming like 453 mm. And when I did the time history analysis, there is a huge difference. I'm getting like 15 mm in time history, while as an equivalent static method, I am getting 453 mm. So I am a bit confused. Am I doing errors or such kind of difference? I want to know basically how much is difference is permissible between static method and time analysis, and is it valid, or I should focus like the key aspects.
Okay, so let me summarize that question in very brief. She has designed one building. It's a 60-story structure, which is a flat slab system with a core shear wall and an another coupled wall system. She done 2 types of analysis. One is equivalent static method, and second is the time history analysis. So when she is comparing the displacement as an output, she is getting a lot of difference between the displacement values when she is comparing with these 2 methods. So her question is why there is so much of difference coming, or whether I'm doing anything wrong in the analysis.
Nothing wrong. Actually, definitely, 2 different systems will have different
Yes.
time periods. and especially if you have a flat slab structure, you have to be very, very careful because flat slabs are vulnerable to punching failures also. Um and also, actually, our IS code does not advocate such flat slab structures in high seismic zones.
Okay.
So better adapt the system which is having less deformations.
And the another thing is there any clause or guideline which says that if you do the analysis by equivalent static method and if you do the analysis by time history, how much difference is permissible between these two methods? I don't think, yeah.
I don't think that is a thing.
Okay.
Of course, earthquake engineering is a very large
Vast. Right.
area,
Absolutely.
and all the people will not know all the aspects of earthquake engineering. It is better to have shear walls to reduce the deformations. That is the best system.
Okay.
In any system, it is better to have shear walls. Of course, in India, there is no concept of steel shear walls, whereas steel shear walls are adopted in USA. They can also be adopted, which can be easily replaced than the concrete shear walls.
Thank you. I hope, Nisha, your question is clarified because sometimes it's very difficult to understand without seeing the model why there are a lot of differences coming between your analysis results. Okay. Still, if you have any doubt, you can write a message or drop an email to Dr. Subramanian sir, and he will definitely respond to you.
And of course,
Yeah.
I don't have any software package. So
Right.
if you ask any specific question regarding a software, I will not know because
Yes.
I am not
Yes.
using any software package.
Okay. Okay, sir. Okay.
I only know the
Thank
concepts.
you, sir.
Okay, thank you, Nisha. So the next question is, it's just a clarification. Although both the robust design and the earthquake resistant design aim for resilience, right? But what is the fundamental difference between these two design methodology? One, same building, if one go for a robust design and one go for an earthquake resistant design. Is there any fundamental difference between these two methodologies?
Yeah, robust design, as I explained, it will reduce the damage.
So the damage is also are varying, right? It can be minor damage, moderate damage, or it is only for a significant damage.
Yeah, if you are using code-based design, if there is an unexpectedly high earthquake force, then you will see a lot of damage. Whereas if you are using a resilient design or robust design, the damage is very much reduced. On this resilient design, you can replace the damage portions easily.
Okay, sir. There is a question related to base isolation system. The participant says, while using base isolation system, the seismic forces are usually reduced by 20 to 30%. Then in such a case, superstructure part, which is above the ground, shall be designed only for gravity conditions only, or they need to also consider the lateral load part as well?
Actually, you are requested to refer to IS 1883 Part 6.
Yes.
Because that gives details about how to design, how to take the forces, and how to detail the structure when you have base isolation systems.
Okay, sir.
That is easily downloadable. Nowadays, all IS codes are easily downloadable.
Right. Thank you. And there is a question from Mr. Rais Ahmed. Yeah, Mr. Rais, are you there? Would you like to directly ask the question to the speaker? Mr. Rais Ahmed.
Yes, sir. Yes, sir.
Yeah, please go ahead.
Sir, actually, my question was that when we check the soft story check for a building, we check the stiffness ratios of the floors as per the codal provisions.
Yeah,
Hello?
please. Yeah, please go ahead.
Yeah, but the recent Turkish earthquake last year, 2 years back, we have seen number of case studies there. Every building which was having the basement, which was having the lower ground floor as a parking, that got collapsed. So in such a situation, I think will we keep the lower ground floor or the basement floor column sections very heavy to avoid such kind of soft story mechanisms?
Yes. Actually, you in the code itself, it is said. Actually, in the previous codes, it was slightly lenient, but the present code, it is very strict. I think I don't remember exactly. You have to find out the stiffness of the top floors, and then
Yeah,
compare the stiffness of the ground floor. If the
obviously.
difference is less than 0.1% or something, I don't know, I don't remember exactly. According to the code, you should not adopt. So what the solution is, you find out the stiffness of the top floors and provide the same stiffness in the ground floor also, either by having bigger columns or by having shear walls or or bracings, etc.
So we have to ensure the lower ground floors with a bigger column size. If the frame
Yeah.
is SMR
First of all,
frame, if the
try to avoid soft story, or you have to have bigger columns or any other
like
uh, shear wall
like
or bracing or any other thing which will increase the stiffness.
likewise the lower ground floor or the lower floors we are using for the parking, so that we cannot use the infill walls there. So the above the floors we have the infill walls.
Yeah,
So it will
you
be better
see,
to.
I showed one failure of a building in San Francisco.
Yes.
You saw that the column simply t- the
Tilted.
drift was so high in the ground floor alone. The top floors were straight. Only the drift in the ground floor is more. That shows that shows the soft story effect clearly.
Oh, okay. Sir, I have a second question. Can I ask it?
Yeah,
Yeah,
yeah.
please go ahead.
Sir, actually, I am from the Kashmir. We have number of projects here. We are designing the buildings on the slopes. So the slope stability issues are number of here. Like we have to create the protection walls there. We have to create the breast walls there. One more query for this I have: if a building is there having one side 5 floors and the other side having 2 floors, building is casted on the slope. So how the global stiffness of such kind of building we can control?
Yeah, it is very uh,
TDS.
tough because your Kashmir area is high seismic zone.
Mhm.
So
Yeah.
you should not have such buildings which are not symmetrical. That is very difficult. So I don't know. You have to have some bracing systems, shear walls, etc., so that that difference is compensated.
Okay. Thanks, sir.
Okay, thank you, Reis. Sir, the next question is how the overstrength in a structure influence its robustness during an earthquake?
Actually, strength and stiffness are two things
Yeah.
which are to be considered. So
Mm.
strength alone is not important.
Mm.
If you provide only strength, it will fail.
Right.
You have to have enough stiffness also.
Right. So the next question is, can increasing the column size and beam size in the soft story alone reduce damages in seismic events?
Actually, you have to increase the column size,
Okay,
not beam size.
not beam size. Okay, so the last question of the day. So the question says, will buildings ever be truly earthquake proof? What's your thought on this?
Yeah, I showed a graph showing that failure versus wall index
Yeah.
and column index.
Yes.
And you, from that you have seen that most of the collapses are there in the bottom quadrant.
Hmm.
So that shows that many buildings have not collapsed after adopting such things. Especially if there is an earthquake in Japan, you
Right.
will see that not much damage is there.
Hmm.
It is because over 100 years ago, some people have researched and told that you should have robust building. So the failure is less. And even if the earthquake is there in USA, there will be considerably there will be more damages in USA than in Japan, because in USA also, of course, we have adopted the clauses from the US courts where we will have flexible buildings. So whereas in Japan you have robust buildings. The
Right.
same thing is adopted in Chile.
Chile.
So
Chile. Mexico.
in that graph, I showed that in Chile there is the earthquake damage is very less, whereas in
Right.
Turkey and other places
Other parts.
the damages are more. So it depends upon the um, methodology you are adopting. If you are adopting flexible buildings as per the codes, there will be damage. Of course, if the earthquake is what you have considered or less than that, there will not be much damage. But
Okay.
suddenly, because we cannot predict, unfortunately, there is no way to predict the earthquake. Actually, there is a book. I just want to show you that book. I
Oh,
don't know.
the blessings of disaster.
Yeah, this is by Bruno, Professor
Michael
Bruno.
Bruno. Okay.
Actually, this book is like a story. It is not having any equations,
Okay. Okay.
but you should all read this book. Probably you can buy from in your library, so that
Okay,
people
sir.
can you can buy some 2 or 3 copies in the library.
Okay.
It
Nice.
it it, it is like a story, but it is very interesting, and it also shows some photographs
Photographs.
of
Okay.
earthquake effects, etc.
Okay.
But here I forgot the name of the place. It seems 2 or 3 times the earthquake occurred. So people were thinking that the next earthquake is going to come in the same duration,
Area.
but it did not come even now.
Oh.
So people cannot say the earthquake will come in a place irregularly, or whether it will be higher or lower earthquake, and so on.
Okay. Sir, one last point. In Indian code, when we calculate the seismic base shear, or rather horizontal seismic coefficient, the code says Z by 2, I by R, SA by G. Initially, in the beginning of your presentation, you clearly mentioned that we design the structure, especially considering the design basis earthquake, where the earthquake forces are reduced by 50% because there is a factor of 2. Whereas in other codes or guidelines, the factor is 2/3, that
Yeah.
is 67%. So what is the rationale behind these numbers? Because I have never seen any document where it has been mentioned that what is the logic behind these values.
Actually, there is also difference in R.
Yes, based on
So
the structural system.
if we compare that, this two
It
third
is
is
10.
similar to 50%.
Okay. Okay.
If we compare that 2/3 with the R of that code,
So it is again comes out to be 1/10.
yeah.
Okay.
So they more or less they compensated that.
Okay. Okay. No,
And
so
also, unfortunately, till now we are using that 50% of the earthquake. But unfortunately, in the draft code and all, they are increasing the earthquake force like anything, based on probabilistic earthquake.
PSHA.
Uh,
Hmm.
but I am against it. because simply
Okay.
increasing the force alone will not
Will not.
result in less damage.
Mhm.
And one more thing I wanted to tell is I forgot. Okay.
Okay, no problem, sir. I think very soon we are getting the new draft version of IS 1893 for buildings, and also instead of 5 seismic zones,
And
there
one
will
more,
be
wait,
6.
I
Yeah,
remembered.
yeah,
Actually, there is one more factor called importance factor.
yes,
Yeah, actually, in the older codes or the present code, for hospitals and other things, 1.5, and
1.5,
ordinary buildings, 1.
1.
So we know exactly that for important buildings like hospitals, which has to be there
Functional.
even after earthquake, we have to design for more load. But
More
in
load.
the
Yes,
yeah,
yes.
but in the draft code, it is taken as 1 for all buildings. So the concept itself is violated.
Yeah, because in case of the hospitals, more than the structural element, the non-structural element plays a very crucial role. So, okay. Okay, sir. I think we very patiently you have clarified all the doubts of our participants.
Thank you.
Thank you
Thank you.
so much. Nandini,
Thank
it's
you.
over to you. Nandini, it's over to you.
Thank you, sir. I hope the queries of all the participants are cleared. Now I would like to call Mr. Jayant Lodi to deliver the vote of thanks.
Greetings to all. I am Jayant Lodhi, pursuing M.Tech in Computer Aided Structural Engineering at IIIT Hyderabad. It's my honor and privilege to deliver the vote of thanks on behalf of the entire Executive Committee of IS Structure IIIT Hyderabad Student Chapter. First and foremost, I extend our deepest gratitude to our esteemed keynote speaker, Dr. N. Subramanian, for his wonderful presentation and enlightening session on seismic resilient or robust structure. Today's webinar has highlighted earthquake design philosophy, circular spiral columns, failure of infill walls, discussion on IS code for seismic resilient design, detailing of beam column joints and shear walls, seismic moment connection in steel structures, example of resilient components, base isolated system, method to increase robustness, foundation designs. Moving on, I would also like to express our heartfelt gratitude to our faculty advisor, Dr. P. Praveen Kumar, for his continuous guidance and valuable suggestions throughout the planning and execution of this event. A special mention goes to the IT team for ensuring seamless technical support and to the design team for their creative inputs and assistance. I thank our program coordinator, Dr. Sunita Palesari, for her continuous encouragement. I also want to express my appreciation to all the participants for their active involvement and thoughtful questions, which enhanced the discussion and made this webinar a collaborative learning experience. Lastly, I would like to acknowledge the hard work and dedication of the entire team whose collective effort has made this event a success. In conclusion, I extend my heartfelt thanks to each of you for your participation and engagement. We are extremely grateful and look forward to your continuous support in our future initiative. Thank you so much.
Thank you. Thank you,
Thank you.
Jayan. Yeah.
Thank you, Mr. Jain. Actually, I want to appreciate you for conducting such programs. I am reading
Thank you,
about
sir.
them.
Thank you so much.
I'm reading about them in the I-Study
Yeah,
newsletter.
yeah, newsletters. Yes, yes. So the core objective is to disseminate the knowledge as much as we can, so that
Good.
the students not only they will learn from the syllabus or the curriculum, but also they should get to know what are the latest updates in the current structural engineering fraternity. So this can be a great platform for them, sir.
Yeah, for all of us, it is important to keep in touch with the subject
Yes,
because
yes,
the
absolutely.
codes are being revised regularly.
Right.
And a lot of research is being done all over the world.
Okay, sir. Thank you so much.
Thank
And
you.
wishing you as well as to all the participants a very happy Holi.
Thank you.
Okay,
Take care.
sir.
All the
Okay.
best.
Okay,
Yeah.
sir. Thanks a lot.